All right, let's go over it. April 26, 1986. Raise your hand if you remember that day. Nice. Well, yeah, right. So maybe you don't remember the day, but I think you've probably heard of Chernobyl, right? It's a pretty famous nuclear disaster. April 26, 1986, I was a lad of 12, and I remember when it happened. The number 4 reactor overheated, exploded, releasing over 100 radioactive elements into the atmosphere. A lot of them short-lived, and they decayed quickly. Iodine, the radioactive iodine, strontium, and cesium were among the most dangerous that were released. They have half-lives, respectively, of 8 days for iodine, 29 for strontium, and cesium was, or 29 years, sorry, and then cesium was 30 years. Okay, so the strontium and the cesium are still present at very, very dangerous levels. Okay, iodine is linked to thyroid cancer, strontium can lead to leukemia, and cesium, the one that traveled the farthest and lasts the longest, affects the body in all kinds of harmful ways, liver and spleen disease, cancer, of course. You might remember this one, 2011, 7 years ago, Fukushima, Japan. Did y'all hear about that one? That's probably the most recent big one that took place. It was very similar in size and intensity to the one at Chernobyl. But there are places in Chernobyl. Chernobyl itself is like a ghost town now. There are probably still a couple people that live in the area that never left. I remember hearing a story about a old man and wife goat farmer that were still living there. They were somehow immune to the radiation. But pretty much it's a ghost town. It's guarded around the perimeter. You have to have special permission to get in. They allow ghost hunters and lead tours sometimes. But if you've ever looked at pictures on the internet, there's like school buildings, and if you go inside the classroom, you could still see their iPads on their desk where they last were working when they just fled. They left everything behind. They took nothing with them. So it's kind of eerie. It's frozen in time. Of course, you walk outside and Mother Nature is slowly taking everything back. The asphalt, has grass growing in it. There's trees growing up through buildings. So it's kind of a hot tourist destination. And if you take precautions or you wear a badge or a hazmat suit, there are ways to visit it, okay? But it's heavily guarded and you need special permission to do it legally, okay? So here's what we're going to do. We're going to assume that 2,000 grams of cesium-137, the atomic weight 137, were released at Chernobyl. I want to know how many grams of cesium-137 are present there today in 2018. How do we start a problem like this? What do we do in the previous examples? Do what? Plug into what? We don't have anything to plug into. Light socket? Oh, we need to write a model, right? So let's use this as the model. A of t instead of y. A stands for amount at time t. So A of t equals, and then the initial amount, we'll call it A sub O. The initial amount is A sub O times B to some t or function of t. All right, so let's see how many of those we know. The amount at any given time, A of t, is. Do we know the initial amount? Yeah, it's 2,000. Do we know what the base is going to be for this radioactive element? Half-life, good. So the base is 1/2 or 0.5. And do we know what the half-life of cesium was? That was the one that was 30, right? When you have things listed in a row and it says 8, 29, 30s respectively, that doesn't mean like we're getting dressed up in a tuxedo to say it. Here are your numbers, sir. It means that those numbers correspond in the same sequence. So 30 years is the half-life of cesium. So what would the exponent be? T over 30. Good. Now off to the side, T is in what units? Years. Good. Now we can decide before we move on if we want to change the units. Is years an appropriate measure of time in this case, or do you want to go millenniums or years? Years would work. Yeah, let's keep it with years. Okay, so if we're going to decide to keep it with years, we have our model. So we have an A value and a T value that we can plug in and find the other one. I either give you an input or an output. So let's answer part A. It says if 2,000 grams were released, how much is left today? So T equals 0 is going to correspond with when this happened. So without looking, what was the date or the year at least? 1986. Good. So that corresponds to T equals 0. So 2018, where we are today, should correspond with T equals what? 32. 32 years later. What's the half-life of cesium? 137? 30, right? So if it started in 2000, a couple years ago, it was the half-life. It was down to 1,000. So our answer should be something a little bit what than 1,000? Less. Okay, so we could check for the reasonableness of our answer. All right, so when I give you T equals 32, do you plug it in for T or A of T? You plug it in for T. So here's what you're going to have to show on any short answer quiz for your response. You're going to have to show me A of 32. If you don't show me that, you can lose points. I'm going to put checks around things that you're either going to get points for or you're going to lose points if you don't have. A of 32 equals. That's all you have to do. Now you go to the calculator. So if you haven't done so already, go to your calculator and in Y1, go ahead and type our function in Y1. So it's 2,000. If you want to use the parentheses, you can go alpha y equals. Remember, alpha y equals gives you your horizontal division bar. And then you can raise that to the, x instead of t divided by 30th power. Now, for the plug and chug variety, we don't need to graph that. So I'm not going to graph that. I'm just going to double check, triple check, make sure it's the right equation. Because we got a lot riding on it, looks good. So now I'm going to get back to the home screen. Second mode, and then flush. There's got stuff on there. So how do I recall from the home screen what's in Y1? Alpha trace. We use trace a lot. Alpha trace or second trace. In this case, it's alpha trace. My equation's in 1. And then just like function evaluation, what's already written on my paper, you should always get in the habit of writing it down on your paper first before you go to the calculator. Y1 of 32 is the same as A of 32. We hit enter. And then how many decimals do we report? 3. Unless it says to round to the nearest whole person, whole year, you always report 3, round or truncate. I'm going to truncate and call it 841. All right. What would the units be? Grams, right? Grams. So that would be a check for the number possibly and the units. Is that a reasonable answer? Very reasonable. We suspected it would be slightly less than 1,000. So that's an indication that we're doing it right. Yes, Cindy? Uh-huh. No. That was just telling you that a lot of stuff got blown out. We are focusing right now on just one element, one isotope, cesium-137. Yeah. I gave you 2 others that were pretty important, the strontium and the iodine, but we're focusing on cesium right now. Okay? Yeah, so the only number that we used was this 30 years up here. That was the half-life for cesium. So yeah, if you have more information in the problem, you have to know how to read through it and figure out what's relevant. Okay, any questions on that? Y'all think y'all could do that? I know you can, right? Good. Let's do the second question. If 20 grams is considered to be a quote-unquote safe level, right? You can go in, but I still ain't going in. After how many years will it take for that cesium to reach that safe level? All right, so 20 grams is considered safe. Is 20 grams a T value or an A value? It's an A value. So this would be the other way to use these equations. In this case, you have to show me that you're setting the function equal to that. And you don't even have to actually write the expression that is equal to the function. You could just use its name, A of T. That's a check. That tells me what equation you're solving. You write that down first, and then you go to the calculator. So now we'll go to the calculator, and in Y2, we sketch 20. Now, because we're sketching it, we need the graph to be good. We want to find where it intersects. So now let's go to the window and think of a reasonable window. X-min, we're measuring time on the x-axis. So 0 is fine. I like to put -1 so I can see the y-axis. The x-max is the one that you might have to adjust, play around with. We're measuring in days. How many days do you want to go by? 300, no, I'm sorry, years. We're measuring in years. You want 300 years to go by? That's not bad. I'll leave it at 300. That's 10 half-lives, right? Let's just leave it like that for a while. We'll adjust it. X scale, you can leave it 1. Y-min, we're measuring grams of cesium. It's never going to be 0. I like to put -1 again so I can see the x-axis. The maximum, 2,500, that's not a good number. We started with how many grams? 2,000, and then it's only going to get smaller from there. So maybe 2,500 isn't bad. 2,100 maybe, a little bit, bigger than 2,000. I'm going to hit graph. Okay, so I do see my decay curve here. It looks pretty nice. Now, if you're only graphing in one color, like most of y'all are, you probably don't see it graphing y equals 20 down at the bottom. But that's fine. Okay, if you don't see it, hit the trace button. Notice at the top of your grapher, it tells you what equation you're on. Right now, we're on the exponential. If you toggle up or down, it'll throw you on the other one. Notice it says, hey, now I'm on y equals 20. So you know it's there. So do what we've been doing. You don't have to change your window at all. Just hit second trace now. Number what? 5. Is this the first curve? Sure, hit enter. Is this the second curve? Yep, hit enter. Guess? Please do, calculator. And even though you can't see it, it'll find it because it's there. So underneath A of t, you put t equals 199.315 or 316. And what are the units on that? Years. Good. So what would you get credit for? The original equation, t equals 199 in years. I may not give you 4 checks for that, but if you're missing any one of those 4, you're going to lose a check for sure. Okay? Remember the common error that I told y'all about. Don't just say A of t equals 20 and then put that equals 199. Because I would probably take off 2 checks for that. One, because 199 is not an A value, it's a t value. And secondly, it's not equal to 20. So that's doubly lying. Don't do that. A of t equals 20 when t equals 199 years. Okay? So that's, if you could do those 2 right there, you've got it all figured out for the calculator. You know how to handle it if you're given an input, and you know how to handle it when you're given an output. The only thing that varies is the equations, the numbers, the situations. That's it. That's how you do those types of problems. Okay? All right, so for what it's worth, Twitter is a real thing, right? Some of y'all are on Twitter. I'm on Twitter. I follow this one account called Chernobyl Status. It's pretty interesting here. This is what they're building right now. It's a huge undertaking. They're building this containment safe at the Chernobyl website. They're building it off-site, though. It's this huge, large, concrete fortified structure that when it's completed, they will push it into place. And the idea is you cover up the reactor and the radioactivity will be contained inside, giving the stuff that's already been released time to decay, because it's still emitting things, okay? So that's a huge undertaking right there. But here's why I follow it. This was 1 hour ago. Chernobyl right now is currently 1.0844% safe. It updates regularly, and we're talking like way down in the decimals. Only 1% safe, all right? I'll go ahead and like that. I don't want that on my timeline, so I'll just like it. All right, cool. So not very safe to be at Chernobyl, right? Not very safe to be at Chernobyl. Okay, if you look up here in their heading, it's in their bio, it says, it'll take Chernobyl 3,000 years, 3,000 years to be safe again. Wow, that's a long time, okay? Can't wait to start rebuilding and making Chernobyl come back to life. I usually don't follow accounts that follow nobody back. It's kind of a one-sided affair there, but it's kind of interesting. Every day I'm so excited to see how the decimals change, right? Okay, anyway, 3,000 years. Any questions on that one? All right, so what I'm going to do is skip number 11 because number 11 requires logs. And we haven't done logs yet, so I probably need to put that in the log section. Log section. But here's what I want you all to do. Example 12, yeah, I'm not going to test you over that either. Example 12 is what I want you all to do, because this one is going to be very, very similar to the titanium bracelet one that we worked the other day. This is what your quiz tomorrow is going to be over with the calculator. This is what your free response question will be on Thursday on your test, which is 50% of your grade. Okay. Now, this one also, like the Chernobyl story, is ripped from the headlines. This is a true story. In 2009, you might remember, we had swine 09. It affected a lot of people in MBISD. Y'all were in little school. We were handling it up here, okay? Here's what I want you to remember about a logistic equation before I cut you loose on that. I'm going to give you about 10 minutes to do it. A logistic equation looks something like the following, or the graph, logistic graph. If it's growth, it's going to increase like an exponential function. It's going to have a y-intercept, and it's going to increase. The only thing is it's not going to continue to increase forever, remember? Not all things can do that. So what's going to happen is after a certain point, it's going to continue to increase, but at a decreasing rate, and it's going to taper off towards this upper horizontal asymptote that we call L. L for limit to growth, or the carrying capacity. So when we did the titanium bracelet example, we were trying to spread the rumor around campus. And so our limit to growth was the size of the campus. I think it was 2,000 students. Okay? These functions also have a horizontal asymptote on the bottom at y equals 0. The only thing is when we apply these to first quadrant solutions, we don't really see that horizontal asymptote because we start at t equals 0, and we only see this part of it right here. All right? But the graph itself continues on. Now, the last thing I want to remind you of is this value right here is called the inflection value. That's where the curvature changes from curving up to down. That's where the function goes from increasing at an increasing rate to increasing at a decreasing rate. That is also where it is growing the fastest, because that's where the curve is the steepest. We don't know the time value where that occurs. We can find it later, but we always know what the y value is where it occurs. What is it? Look at it visually. Where did I draw it? Halfway, right? Between 0 and L. Between 0 and L. So this is always at L halves. It's always growing the fastest when the y value is half the carrying capacity. That's super important. Now, how do we know what L is? Well, let's scroll up here. I deleted it, but this is what we're going to do. This is the template for a logistic equation. L is always right there in the numerator. He's standing by himself in the numerator. Here I am. I'm the limit to growth. I'm the horizontal asymptote at the top. So half of that number is where it's growing the fastest. So in this example that I'm about to let you do, what is our L value? 2,200. So how many students have been infected with the flu when it's growing the fastest? Half of 2,200, 1,100. Okay. So with that in mind, or with that priming L's pump, with the calculator, go ahead and do example 12. If you remember what I said last time, get this into your calculator into Y1, check your window, and don't start answering questions until you see an S-curve, okay? Because if you don't see the S-curve, something's wrong. Your window's wrong. You typed it in wrong. Make sure you see the S-curve before you start answering questions, okay? I will give y'all